the fourth video in section 410, antiderivatives. Hi, it's Mrs. Allen, and I wanted to recap on example 5 for just one item that I thought I went through a little bit fast. That recall there was this step that we did in step 6 where we said the second derivative was the same as the second derivative of capital F of x was equal to the first derivative of f. So if I wanted to look down here and you thought, I don't know what was going on when she did this, let's recap on that. So that we found that the graph of f was concave up from 0 to 2 and 4 to infinity. And then it was concave down from 2 to 4 because we found that the second derivative carried the same sign as the first derivative of lowercase f. So let me say that again. The second derivative of capital F was the same as the first derivative of lowercase f. And here's the definition that we had started off with, that if a function f is called an antiderivative of f, and this was on the first part of your notes, on an interval I, a function f is called an antiderivative of lowercase f if, on an interval I, if f prime of x is equal to f of x for all x in I. So if you saw that we had f prime of x, then let's take the derivative again of both sides, and you can kind of see if that was equal to then the derivative with respect to x of f of x, lowercase f of x on the right hand side, then we would get capital F double prime of x then would be equal to lowercase f prime of x. And we were able then to tell what the concavity of the graph of f was. So just wanted to recap on that from the definition with the antiderivative, capital F. So next, so this little guy is a little bit happier than I guess that he has figured out the solution to his problem. Yay! So now we're going to be dealing with another problem, and it has to do with slope fields. So we're given the problem if f of x is equal to the square root of 1 plus x cubed minus x. We want to sketch the graph of the antiderivative, capital F, that satisfies the initial condition f of negative 1 is equal to 0. Now, we can't really take the antiderivative of lowercase f of x, so we're going to have to work with what's called a slope field and kind of sort of approximate what the function capital F of x would be. So we're going to draw a direction field for this. So we will draw what we call a direction field. A direction field, or oftentimes we call it a slope field. This is an AP strand that we need to deal with, and I thought I'll insert something here. So the first thing I'm going to do is I've got some information. I know that f of negative 1, capital F of negative 1 is equal to 0. Now I know on your notes you have a graph, and I've got my graph covered up at this point. So that means you guys are going to pause the video and you're going to be drawing some of the graph. But let's get this information organized first. So we know that we have the point negative 1, 0 on the graph of capital F, the antiderivative. Then if we look at this, then it says we have the function f of x. So let's look to see what this looks like. F I'm going to treat like the slope, because remember that f of 0, or f of x is the function, so if I take the antiderivative of f, think of it like f is the derivative, antiderivative would be a function. So now f of 0, considering that, I treat it like the slope, and I'd say, okay, the square root then of 1 plus 0 cubed minus 0 would be equal to then 1. Since capital F prime, or the slope, is equal to f, according to the definition we just went over, then that would tell me the slope, at x equal to 1 is always 1. And so at x equal to 1, it doesn't matter what the y value is, the slope will always be 1, because if you look at your function of x, your function of x is dependent only on x and not y. So considering one more, what you would do then is you would draw short tangents. Now I'm going to pull this away just a slight bit. Well, I might have to pull it away a little more than a slight bit. So you can see that if you look at my slope field here, let's look at x is equal to 1. So if we look at x is equal to 1, here it is, the slope is always 1. Now, I think I was drawing them on a little bit. Oh, I'm sorry, the slope at 0 is always 1. So if you look at here, and I'm starting off at the point 0, 2, and I'm looking up to this point. So at x is equal to 0, all the slopes are then equal to 1. So you can see that down here. Now, what I'd like you to do is we go back and forth. Now, if you can pause the video and now go back and see if you can draw all of your little tangent lines at each x value. And as you go vertically at each value of x, the slope should be the same. I have a table below here, so I've already figured out the slope values. Remember, the slope of f of x is in the table, so you can go back, pause your video, and since f prime is equal to the function f, we'll be looking at f as the slope of our antiderivative graph. So go ahead and graph, pause your video now, and graph your slope field. So we could continue this process for x is equal to all of the values that you see, -1, -0.5, x is equal to 0, 0.5, 1, 1.5, 2, 2.5, and 3. So for all of those values, we would draw little tangent lines that represent the slope. At each coordinate point. Okay, so if you look at this then, let me click on this so you can see what it looks like. This is what your slope field looks like. I kind of think of it like a flow, like almost like a fluid that's got a flow at different points. So if you picture, let me get a nice big color here. Let's go red and maybe a little thicker. Okay, so if we start down here at -1, it almost, now picture it like a river flowing. And it looks like it kind of flows, if you will, kind of up. And look, it has the slope coming up, levels off a little bit, comes up. Look, and I'm going to go with the slope here. And then it looks like it gets steeper as you head out. So my slope field will allow me to get an initial position. That's kind of off right down here. But again, it's like, you know, an approximation on a graph. So if you see at -1, it looks like the slope is 1, so maybe a little bit less steep here, but I think we're all right with just estimating. This would be a specific f of x, a specific antiderivative with the initial information starting at the point 0, -1, 0. Okay, so you can see that you could also have other specific graphs drawn up there, but you would see, like, if I started down here, let me go highlight around this, and let me see if I can do green. So if I started here at this point, you could see that you might draw something like this as it levels out, and again, steep on that side. So this is the slope field for a family of functions where we're graphing the antiderivative, capital F of x, of the function lowercase f of x. So this is a topic that we will revisit in Chapter 10 in Calc 2. Okay, so let's try this next example. A car is traveling 50 miles per hour when the brakes are fully applied, producing a constant deceleration of 22 feet per second. What is the distance covered before the car comes to a stop? So, in this one, we're looking at the fact that we have an acceleration that's kind of talked about. We have a deceleration. So we would have acceleration. The first thing I would note is starting to pull out the information. Acceleration is equal to negative, maybe I should write that as acceleration A of t. A of t is equal to negative 22 feet per second squared. And then I note that, well, then I have miles per hour too. I may want to change the miles per hour. But for right now, let's do that over here. We've got v of 0. V of 0, it's spoken about. That is the initial time. When t is equal to 0, t equals 0, v of 0 is 50 miles per hour. 50 miles per hour. And 50 miles per hour when the brakes are fully applied, but we have acceleration in feet per second squared, so we're going to change velocity, 50 miles per hour. We're going to multiply by 5,280 feet in 1 mile. And then we're going to multiply by 1 hour over 3,600 seconds. So then we have v sub 0 in the units that we like. V sub 0 is equal to 220 over 3, and that would be in feet per second. As you can see that we have miles cancel, and then we have hours cancel, and our units are feet per second. So now we have the initial velocity. Okay, so the initial velocity is 220 feet per second. Now, we start with acceleration. We're going to do a couple things before we get to the next video. The second thing is that we know that velocity, v of t, then is going to equal the antiderivative of a of t. A of t dt. Oh, my goodness, I just stepped ahead into the integral notation. We haven't used it. So v of t is the antiderivative of a of t. So v of t, take the antiderivative, remember we're going backwards because a of t is the derivative of v of t. So now we're going backwards. So we have that the velocity is then negative 22t plus an arbitrary constant c. But we know now that v of 0 is then 220, we'll leave the units off for right now, over 3 feet per second, so is equal to negative 22 times 0, v of 0, plus c. So now we would get c is equal to 220 over 3. So we have our c. So then we're going to say our velocity then, I'm going to change color here so we can pick up on the next video. We have our velocity function then is equal to negative 22t plus 220 over 3. So now we have our velocity function. We'll pick up on the next video and we'll continue with this problem on acceleration, velocity, and we want to find the distance that the car covers before the car comes to a complete stop. Hang on.
See you in a minute.